In everyday life, people relate one thing to another. For example, the weight of a healthy person can be related to his height. That is, the height of a person can be paired with his weight. These readings can be built up as a list. 157.5 centimeters, 58 kilograms. 167.64 centimeters, 62 kilograms. 180.34 centimeters, 67 kilograms, and so on. Again, distance traveled by a car moving with uniform speed of 60 kilometers per hour can be paired to the time taken to travel a certain distance. These readings too can be built up as a list of 1, 60, 2, 120, 3, 180, and so on. And lastly, the weatherman of the city relates temperature readings to the day of the week. That is, each day of the week is paired with the average temperature reading of the day. List of these readings is built as follows: 1, 40, 2, 42, 3, 38, and so on. These two readings make a lot more sense if paired together as shown here. In all these cases, we have paired the numbers representing a set of information. In our first case, the first number in the pair corresponds to the approximate height in centimeters, and the second number corresponds to the weight in kilograms. Similarly, in the second case, the first component is the time taken, and the second component is distance in kilometers. And finally, in the third case, first component is the day of the week, and second component is the temperature of that day. Here, the order in which the numbers are grouped is important. A wrong order or grouping will lead to confusion. These pairs of numbers that are grouped in a particular order and written in this particular format are called ordered pairs. These ordered pairs form the basis for the study of the mathematical concept of relations and functions, which in turn is the basis of study of calculus. Let's learn about these ordered pairs and their properties. Let's see the three cases considered in the beginning. Notice that in all these cases, information from one set is paired with another. By generalizing this, we may say that an ordered pair is a pair of two elements taken from two sets grouped together in a particular order. The elements of the ordered pair are written within the parenthesis and separated by comma. Let us define an ordered pair mathematically. Let A and B be two non-empty sets. If A is the element of A and B is the element of B, then A, B is called an ordered pair where A is the first element and B is the second element. It is evident from the definition that ordered pair A, B is not the same as B, A. Note that only parentheses or round brackets can be used to represent the ordered pairs. We cannot use curly brackets to denote an ordered pair. The notation of curly brackets is reserved for the sets. Remember, when we deal with sets, the order in which the elements appear is not significant. But for ordered pairs, the order in which the elements appear is important. Now, can we have two ordered pairs to be equal? Well, two ordered pairs will be equal if their corresponding first elements are equal, and the corresponding second elements are also equal. Thus, the ordered pair A, B is equal to the ordered pair C, D if A equals C and B equals D. On the other hand, if ordered pair A, B is equal to the ordered pair C, D, then we can conclude that A equals C and B equals D. Therefore, we can conclude that the ordered pair A, B is equal to the ordered pair C, D, if and only if A equals C and B equals D. Let's find out which of the following ordered pairs are equal. We know that the ordered pair A, B is equal to the ordered pair C, D on the condition A equals C and B equals D. The condition of corresponding first and second elements being equal is not true for the two ordered pairs in part 1, 2, and 3. But we can see that for the two ordered pairs in part 4, the first elements are equal to each other, and so are the second elements. So, the ordered pairs in fourth part are also equal. Remember what a point in the Cartesian plane is? An ordered pair, as first element corresponds to the distance along x-axis and second element as the distance along the y-axis. So, we can represent every ordered pair as a point in the Cartesian plane. In the ordered pair A, B, the first element, that is, A, is the x-coordinate, also called the abscissa, and the second element, that is, B, is the y-coordinate, also called the ordinate. In fact, the first and second elements may also be called the first and second coordinates. Let's plot some ordered pairs in the Cartesian plane. We can see that the points 2, 3, 3, 2, minus 2, 3, 2, minus 3, and minus 2, minus 3 are all distinct points in the plane. Let's now apply the definition and concept of equality of ordered pairs to solve some problems. Suppose a person has 4 shirts and 3 pants. How many attires can he make out of it? Is it 3, 4, 7, or 12? Well, to find the answer, let's name the shirts as S1, S2, S3, S4, and pants as P1, P2, and P3. Now, S1 can be paired with any of the 3 pants P1, P2, or P3, and so are the shirts S2, S3, and S4. So, the possible combinations are S1 P1, S1 P2, S1 P3, S2 P1, S2 P2, S2 P3, and so on. Totally 12 attires can be made with the existing 4 shirts and 3 pants. In this process of pairing, we are actually making use of the concept of Cartesian product of 2 sets. Let's learn about the operation of Cartesian product of sets. Now, in the scenario of making attires out of 4 shirts and 3 pants, let us bring some mathematics and see how this is related to Cartesian product of sets. Let A be the set of shirts and B the set of pants. We take the first shirt and pair it with the 3 pants. Then take the second shirt and pair it with the 3 pants, and similarly the third shirt and the fourth shirt paired with 3 pants each. In this process, we are getting the ordered pairs in which first element comes from set A, that is, set of shirts, and second element comes from set B, the set of pants. This is nothing but finding Cartesian product of set A, the set of shirts, and the set B, the set of pants. It is written and read as A cross B. Let us now generalize the concept of Cartesian product for any 2 given sets. The Cartesian product of two sets is the set of all ordered pairs for which the first element is a member of the first set and the second element is a member of the second set. Notice that to obtain Cartesian product of the sets, we do not multiply elements as we do in the multiplication of numbers. Instead, we pair elements together. Using symbols, the language of math, Cartesian product of two non-empty sets, P and Q, that is, P cross Q, is the set of all ordered pairs of elements P, Q, where the element P is from set P and the element Q is from the set Q. Cartesian product of two sets is also known as the Cartesian product set or simply the product set. Cartesian product of sets helps us to find the possible pairs that we can generate from two sets. For instance, a deck of cards obtained is nothing but the Cartesian product of the set of ranks and suits. The set R cross S gives the entire deck of 52 cards. Let's now explore some properties of Cartesian product and see whether it's similar to the product of numbers. Notice that in order to find out the Cartesian product, we need two sets. So, Cartesian product is a binary operation. Recall that an operation that involves two operands is called a binary operation. For example, intersection or union of two sets are binary operation, whereas the complement of a set is unary operation. Let us now find the Cartesian product of two given sets, A and B, for a better understanding. We begin by taking the first element of the first set, A, and pair it with every element of the second set, B. Then we take the second element of the set A and pair it with every element of set B. Lastly, we take the third element of set A and again pair it with every element of set B. By doing so, we have obtained all possible ordered pairs whose first element belongs to set A and the second to set B. Notice that Cartesian product of two sets is also a set with elements as ordered pairs. That is why we separate elements by commas and enclose them by curly brackets. Now for the same sets A and B, let us find the Cartesian product B cross A and check if the two Cartesian products are the same. The Cartesian product B cross A will be the set of all ordered pairs of which the first element is a member of the second set B, and the second element is a member of the first set A. So by pairing the elements we get the set B cross A as shown. We can see that A cross B and B cross A are not equal. Unlike the product of numbers, Cartesian product of two sets is not commutative. Now we know how to find the Cartesian product of two sets with ease. Shall we move further, where we have to perform operations on more than two sets first, and then find the Cartesian product? Here, we are given three sets, A, B, and C. We have to check whether the set of ordered pairs given is the Cartesian product of A intersection B and B intersection C. We will first find out A intersection B and B intersection C. Next, we take the two elements of A intersection B and pair them with the element of the singleton set B intersection C. Note that order of elements is the requirement of an ordered pair and not that of a set. As we know, the order of elements in a set is not significant. Therefore, the set of ordered pairs given is the Cartesian product of A intersection B and B intersection C. Let us see the definition of Cartesian product of two sets, P and Q, once again. According to the definition, both the sets P and Q are non-empty sets. What if either one or both the sets in consideration are empty? Consider the case when Q is empty. We do not have the set to give us the second element of the ordered pairs. And similarly, if P is empty, then we do not have first elements of ordered pairs. So if either P or Q is a null set, then P cross Q will also be a null set phi. Same holds true when both P and Q are empty. In other words, we can say that the Cartesian product of a non-empty set with an empty set or of two empty sets is equal to an empty set. Now, what if one of the sets is infinite? Can we find the Cartesian product in such a situation? Let's understand this with an example. Let the set P be the set of natural numbers 1, 2, 3, and so on, and set Q has elements A and B. So the Cartesian product will have the ordered pairs 1, A, 1, B, 2, A, 2, B, 3, A, 3, B, and so on. That means the set has infinite ordered pairs. Therefore, we can conclude that the Cartesian product is also infinite in case of one of the sets is infinite. It may also be noted that if we can find the product of a set with itself, just like we can multiply a number with itself. For example, if A is a set with elements 1 and 2, then A cross A would be equal to the set of ordered pairs 1, 1 and 1, 2 and 2, 1 and 2, 2. You must be wondering why A cross B is called Cartesian product. Do you want to know why it is so? The Cartesian product is named so after the Cartesian plane. Recall the coordinate geometry and the Cartesian coordinate system. Points are represented in a Cartesian plane as ordered pairs. In fact, the entire Cartesian plane is simply the Cartesian product of the set of real numbers R with itself. Since R cross R describes the Cartesian plane, this product is called Cartesian product, and the Cartesian plane was named after its discoverer, René Descartes. One day, while lying on the bed, the French mathematician solved the problem of describing the position of a point in a plane and laid the foundation of Cartesian plane. Just as the Cartesian product R cross R represents the coordinates of all the points in the two-dimensional plane, the Cartesian product R cross R represents the coordinates of all the points in three-dimensional space. The triplet x, y, z is called an ordered triplet. This shows that Cartesian product can be extended to three sets as well. Let us now define the Cartesian product of three sets. The Cartesian product of three sets is the set of all ordered triplets for which the first element is a member of the first set, the second element is a member of the second set, and the third element is a member of the third set. By using symbols and the language of math, Cartesian product of three non-empty sets P, Q, and R, read as P cross Q cross R, is the set of all ordered triplets of elements P, Q, R, where the element P is from set P, the element Q belongs to set Q, and the element R belongs to set R. When A and B are non-empty sets, then how many elements does the product set have? Is there any way by which we can find the number of elements without actually finding the product? To understand, let us consider the Cartesian product of two sets. When the set A had 3 elements and the set B had 4 elements, the number of elements in the Cartesian product of the two sets was 12. This is justified too because each of the 3 elements of A is paired with each of the 4 elements of B, giving rise to 3 times 4, that is 12 elements. By generalizing this observation, we may say that if there are P elements in set A and Q elements in set B, then there will be PQ elements in A cross B. In other words, cardinality of the Cartesian product of sets is the product of the cardinalities of given sets. This holds true in case of one of the sets is empty or infinite. We have seen that the Cartesian product of sets is a set whose elements are ordered pairs. Recall that the set can be represented algebraically in roster form or set builder form. For example, the set A of squares of natural numbers can be represented in roster form by listing the squares of natural numbers, and in the set builder form by using definition x such that x equals n square, where n is a natural number. We have seen that sets can also be represented graphically using Venn diagrams. So out of these ways, in how many ways can you represent the Cartesian product of sets, which is a set again? Well, both algebraic and graphical modes are applicable to the Cartesian product of sets as well. Let's explore the various ways of representing the Cartesian product of sets here. Let's first explore the algebraic ways of representing the Cartesian product of sets. The Cartesian product of sets can also be represented by both the roster and the set builder methods. For example, consider the sets A and B with elements 3, 5, and 2, 4, 6, respectively. By definition, the Cartesian product of sets A and B is A cross B, the set of all ordered pairs of elements A comma B, where the element A is from set A and the element B belongs to set B. This, in fact, is the set builder form of representing the Cartesian product A cross B. We can easily write the Cartesian product of the given sets A and B in the form of ordered pairs 3, 2, 3, 4, 3, 6, 5, 2, 5, 4, 5, 6. This is the roster form of the Cartesian product A cross B. Did you realize that we have written the same Cartesian product A cross B in two different forms, in roster form and set builder form? So which of the two forms is more suitable? As we can see in our example, both forms are suitable. When the number of elements in the sets is not too large, it is simple to write the Cartesian product in either of the two forms, the roster or the set builder form. But when the cardinality of sets is large or the sets are infinite, representing the Cartesian product in set builder form is more efficient. Let's now represent the Cartesian product of two sets in both these forms for practice. Given two sets, we need to find A cross B and B cross A in roster form and in set builder form. Let us first write A cross B in roster form. We know that A cross B will have all the ordered pairs obtained by pairing the elements of A with those of B. So taking 7 first and pairing it with 5, 4, and 2, and then taking 8 and pairing it with 5, 4, and 2. Now we use the definition of Cartesian product to write A cross B in the set builder form as shown here. Next, to write B cross A in roster form, we take every element of set B and pair it with every element of set A. For B cross A in the set builder form, we use the definition of Cartesian product again. Consider this next example. Given a set A with elements M and N, we are to write the Cartesian product of the set A with itself in both algebraic forms. Let us first write A cross A in roster form. We pair element M with element M and with element N. Next, pair element N with element M and with element N. Now we use the definition of Cartesian product to write A cross A in the set builder form. Let us now see how to represent the Cartesian product of sets graphically, first in the Cartesian plane. Recall that we can represent every ordered pair as a point in the Cartesian plane. The first and second elements of the ordered pair are the abscissa and the ordinate, respectively. This diagram is also called a lattice, and each point marked to represent an ordered pair is called a lattice point. Let us represent the Cartesian product of the two given sets graphically in the Cartesian plane. Let us take a Cartesian plane. Now, let us plot each ordered pair of the Cartesian product on this plane as normal. Let us learn one more method of representing the Cartesian product graphically. This method is called the arrow diagram. In this method, we first use a Venn diagram to represent the two sets A and B. Then we use arrows connecting the first component of the ordered pair in set A to the second component of the ordered pair in set B. Let us take the Cartesian product of the same two sets as in the previous algebraic and graphical representation and represent this Cartesian product using the arrow diagram. We begin with the Venn diagram representing the two given sets A and B. We draw arrows from the first component of every ordered pair in set A to the second component of the same ordered pair in set B. That is, we draw one arrow from element 3 in set A to element 2 in B. Then, we draw an arrow from element 3 in set A to element 4 in B. Then we draw an arrow from element 3 in set A to element 6 in B. Now we draw three arrows going from element 5 in set A to each of the elements 2, 4, and 6 in set B. Recall that the Cartesian product of two non-empty sets, P and Q, is the set of all ordered pairs whose first member is an element of set P and whose second member is an element of set Q. It is called a product, but here we do not multiply. We just pair the elements. So, if sets P and Q have x and y elements each, then the product set P cross Q will have x, y elements. Just as in the multiplication of real numbers, a Cartesian product can also be extended to three sets. That is, if P, Q, and R are three sets, then P cross Q cross R is the set of all ordered triplets that has its first element from set P, its second from set Q, and its third from set R. Do you think the Cartesian product will satisfy the properties, such as the commutative property, the associative property, and the distributive property, that are satisfied by the multiplication operation? Let's find out by taking some examples, and also solve some more problems based on the concept of the Cartesian product of sets. In everyday life, we frequently speak of relations between two objects or living beings. For example, in case of human beings, we might talk about relations such as father and child, brothers, sisters, brother and sister, student and teacher, etc. In the case of countries, we have relations such as adjacent countries, trade partners, etc. Likewise, there are relations in mathematics as well. Amongst numbers, we talk about less than, more than, equal to. Amongst line segments, we have perpendicular to, parallel to, intersecting, etc. Similarly, in set theory, we have subset and superset relations. Did you notice that in all these cases, relations indicate the existence of certain connections between the pairs of objects? Let's look into the mathematical relation of one non-empty set to another non-empty set in detail. Let us take two sets, a set A of some children, say Ashish, Rita, Mary, Fatima, Rahul, and a set B of their fathers, say Mohan, Sunil, David, Kareem. Let's represent these sets as Venn diagrams. Now, let's map each child to his father. Say Ashish is the child of Mohan. So we map Ashish to Mohan. Let us write that as an ordered pair as well. Similarly, we represent the other child-father pairs. Now, this set of ordered pairs that has emerged is the relation described as is the child of. We can call this relation R. Now, we can write the Cartesian product of the two sets A and B as follows. Did you notice any relation between the sets R and A cross B? We can see that all the ordered pairs in R are also there in A cross B, so R is the subset of A cross B. We will use this to define a relation mathematically. A relation R from a non-empty set A to a non-empty set B is the subset of the Cartesian product set A cross B. This subset is derived by describing a relationship between the first element and the second element of the ordered pairs in A cross B. Recall that in the case of a set A, a null set is a subset of every set, and every set is a subset of itself. So also in the case of a Cartesian product, because a Cartesian product is after all a set. So two obvious subsets of A cross B are A cross B itself and the null set. Are these relations as well? Let us find out. By definition, both the null set and the set A cross B itself are relations as well. In fact, these are special relations. The null set phi is called a void or empty relation. Here no element of a set A is related to any element of set B. The relation is a sister of in a boys' school is an example of an empty or a void relation. Since the school is a boys' school, no student in the school can be the sister of any other student in the school. Hence, no two students are related in this way. Another example of an empty relation is the relation is the square of from a set of negative real numbers to another set of real numbers. Recall the square of a number is always a positive number. Next, the entire set A cross B is called the universal relation. In this relation, every element of set A is related to every element of set B. There is one more special relation from a non-empty set to another non-empty set known as identity relation. If every element of a non-empty set A is related to itself, the relation is called the identity relation on A and is usually denoted by IA. So, how many relations can be defined from a particular set A to set B? A relation from a set A to a set B is a subset of their Cartesian product. So the number of relations from set A to set B will be equal to the number of subsets of A cross B. Recall, if there is a set A with P elements in it, and the number of elements in set B is Q, then the number of elements in the Cartesian product of A and B will be PQ. So the number of subsets of a set with PQ elements is 2 to the power PQ. So the total number of possible relations from set A to set B is the total number of subsets of the Cartesian product A cross B, that is, 2 to the power PQ. Let us find the number of relations from set A to set B for the given sets A and B. The cardinality of A cross B is 4. Therefore, the number of relations from A to B will be 2 to the power 4 or 16. Let's now learn some terminology and notations used to describe relations. A relation R from set A to set B is denoted as shown. If an ordered pair A, B is in relation R, then A is related to B or ARB. And if the ordered pair A, B does not belong to R, then the element A is not related to the element B. In an ordered pair A, B, A is the preimage and B is the image of A. The set of all first elements or preimages of relation R is called the domain of relation R. The set of all second elements or images is called the range of R. If R is the relation from set A to set B, then B is called the codomain of R. In fact, any superset of the range will also qualify to be the codomain. For example, from set A having elements 1, -2, and 2 to set B with elements 2, 3, and 4, consider the relation R. The domain of R is the set with elements 1, -2, and 2. The codomain of R is the set with elements 2, 3, and 4. And the range of R is the set 2, 3. Let us begin our exploration with an algebraic representation of relations. We know that a Cartesian product can be represented algebraically either in the roster form or in the set builder form. A relation too can be represented by both these methods. To see how, consider R, a relation from set A which has elements 1, 2, 3, 4, 5, 6, and 7 to set B, the set of natural numbers. Let R be defined in such a way that the sum of the two elements is 8. We can write this relation using the roster method as the set of ordered pairs 1, 7, 7, 1, 2, 6, 6, 2, 3, 5, 5, 3, 4, 4, and using the set builder method, a set with ordered pair x, y such that x plus y equals 8. Here x belongs to set A and y belongs to set B. If a relation is given in any one algebraic form, we can easily convert it to the other form. Let's look further into this with an example. Consider this relation R defined from a non-empty set A to itself given in the set builder form. Let us express it in the roster form. Using the definition of relation, the two elements are related if the latter exceeds the former by 1. So in roster form, the relation has the ordered pairs 1, 2, 2, 3, 3, 4, 4, 5, 5, 6. Now think of this relation from set P to set Q given in roster form. Let us express the relation in set builder form. Notice that the first element in each ordered pair is the square of the second. This observation helps us to write the relation in the set builder form as a set of ordered pairs x, y, where y is the square of x, or x is plus or minus square root of x. Like the Cartesian product of sets, relations too can be represented graphically. Let us now explore the graphical representation of relations. Let's first consider the arrow diagrams. Consider this relation from the set A containing elements 0, 1, 2, 3 to the set B containing elements 1, 3, 5, 7, 9. Relation R from the set A to B is defined as the set of ordered pairs shown here. First, represent the sets A and B as the Venn diagram. Then, mark the arrow from the first element of the ordered pair to the second element. So we get the arrow diagram that represents the given relation. We have seen one method of representing a relation graphically, using an arrow diagram. Let's now see the other way, that is, representation in the Cartesian plane. Relations too can be represented in the Cartesian plane as sets of ordered pairs. These ordered pairs are called the graph of a relation. The graph of a relation R is the set of all points x, y in a coordinate plane such that x is related to y through the relation R. A relation consisting of finitely many ordered pairs of numbers, as in our example, could be graphed by simple plotting of points. Let us now represent this relation graphically. As usual, the first element of each ordered pair corresponds to the x-axis and the second element to the y-axis. Now, a relation may or may not always contain finite points, especially the ones given in set builder form, described using equations. How many points should we plot for such a relation? In such cases, we plot enough points to reveal the essential behavior of the graph. For example, in the case of this given relation, which is a linear relation between x and y, the graph could be sketched by plotting 2 points satisfying the given relation. Let's take 2 points satisfying the relation. Say the points are 0, 2 and 3, 0. Plot them on the plane and then join the line. However, for this relation, we will need to take many more points to ascertain its graph. Let us take some points that satisfy the relation and plot them. Next, we join the points obtained. We get a circle as the graph of the given relation. Taking our discussion to the next level, any graph in a coordinate plane defines a relation in this way. If a point representing the ordered pair x, y lies on the graph, then x is related to y. For example, the given ellipse is the graph of some relation, say R. The point 3, 2 lies on the graph, whereas the point 2, 3 does not. So 3 is related to 2, but 2 is not related to 3. The relation R from a non-empty set A to a non-empty set B is a subset of the Cartesian product set A cross B. So relation R2 will have a set of ordered pairs as its elements. Symbolically, it is written as shown here. Recall that in the ordered pair A, B, A is the pre-image of B, and B is called the image of A. We also know that the set of all first elements or pre-images of relation R is called the domain of the relation R. The set of all second elements or images is called the range of R. If R is a relation of set A to set B, then B is called the codomain of R. In fact, any superset of the range will also qualify to be the codomain. Next, we also know that if there are P elements in set A and Q elements in set B, then there will be PQ elements in A cross B, and therefore there are 2 to the power PQ subsets, and the total number of possible relations from set A to set B is 2 raised to the power the cardinality of the product set. Since the null set and the whole of A cross B are 2 obvious subsets of A cross B, so a null set is called a void or an empty relation, and A cross B is called the universal relation. Another special relation is the relation from a set to itself, in which every element is related to itself, which is called the identity relation on A. Armed with all these concepts related to relations, shall we solve some problems based on them? Consider the four relations shown here. The first one relates a polygon to the number of its sides. The second one relates a natural number to the number that is twice as much. The third one relates an integer to its square. And the fourth one relates children to their fathers. Look carefully at the four relations. Did you notice anything common to all these relations? Well, there are two common points. First, every element of the first set is related to an element in the second set, or every element in the first set has an image in the second set. Secondly, no element in the first set has two images. Summing up our observations, we can conclude that in all these relations, every element of the first set or domain set has a unique image. These relations are called functions. Let's find out about these special relations. We can see that a relation from one non-empty set to another non-empty set is called a function if every element of the first set has an image in the second set and none of the elements has more than one image. We can formulate this as the definition of a function. A relation f from a set A to a set B is said to be a function if every element of set A has one and only one image in set B. From this, we can conclude that a relation will be a function if and only if it satisfies the two conditions. First, all elements of the first set have an image. Secondly, no element has two images. Also note that a function from set A to set B is also called mapping or association from set A to set B. From this, we can conclude that every function is a relation, but not the other way around. Let us now consolidate the knowledge of notations and terminology used in functions. This notation is for a function f from x to y used first by mathematician Leonhard Euler. It is read as f such that x maps to y. It means that f is a function from set x to set y. Set x is called the domain of function f and y is called the codomain of f. By the definition of function, given an element x in the set x, there is a unique element y in the set y that is related to the element x. This unique element y to which f relates x is denoted by f of x. The set of all values of f of x taken together is called the range of f. If you observe closely, a function is like an input-output machine and each input has only one output. And the output is related somehow to the input. So in a function, if you input a value of x that belongs to set A, the relationship, that is, the function, outputs a unique value of y in set B that is related to the element x. Let us take the example of a very simple function. Multiply by 2 and see how it can be related to the input-output machine. Let us input some values of x and check out the output. When the value of x equal to 0 goes into the machine, the output value of f of x is 0. When the value of x equal to 1 goes into the machine, the output value of f of x is 2. When the value of x equal to 7 goes into the machine, the output value of f of x is 14, and so on. These sets of input-output values forms the domain and range of the function. A function can be represented in a variety of ways. It may be represented by a table, roster form, as a set of ordered pairs, an algebraic rule, an arrow diagram, or as a graph comprising ordered pairs in a plane. Let us examine each of these methods, beginning with the tabular method. In the tabular method, a function is a pair of values shown from the left-hand to the right-hand column. Notice that no value is repeated in the first column. The set of values in the first column indicates the domain of the function, and the second column gives the range. Next, let's consider the second form, the roster form. In this form, the function is represented as the set of ordered pairs as shown here. In the roster form, the set of first elements in the ordered pairs forms the domain, and the set of second elements forms the range. Moving on to the third representation as the algebraic rule, if f is any function from set A to set B, then we can write it using the algebraic rule as shown. Consider this function, which maps every natural number to its square. This function can be expressed in the algebraic rule as shown here. It is easy to see the domain and range of the function from this representation of the function as well. These three ways are algebraic ways to represent the functions. Now, let's move on to the geometric methods and see an arrow diagram. In an arrow diagram, the elements of a set are mapped to the other set, such that no element in the first set is left out, and no element is mapped to more than one element. In this representation of the function, the domain is the set of pre-images, and the range of the function is the set of images. The next geometric method is the set of ordered pairs representing the function plotted as points in the x-y plane. In this form, the function is the rule of correspondence from horizontal axis to vertical axis. Here, each number on the x-axis is associated with only one number on the y-axis. Let us plot the ordered pairs representing the function y equals x squared as points in the Cartesian plane. Note that in this function both x and y are natural numbers. If they had been, say, non-negative real numbers, we would have drawn a curve through these points plotted on the xy plane. A function represents a curve which a vertical line intersects only once. We have seen various ways of representing a function in both algebraic and geometric forms. A function, we know, is a special type of relation, and hence not all relations are functions. So, let's find out how to determine whether a relation represented in any of the forms is a function or not. For a relation expressed in the form of ordered pairs, we would say a relation f is a function if no two pairs in it have the same first element. In other words, we can say that if the first element of the ordered pairs is not repeated, then the relation is a function. Let us look at a couple of examples so that we can understand this concept clearly. Given two relations, we have to tell which of them is a function and which is not. Let's look at the first part of the question. The first two ordered pairs in the given set of elements have the same first element, so this relation is not a function. Now, coming to the second part. Here the first elements, 2, 3, 4, 5, and 6, have unique images, so this relation is a function. Further, the set of all first elements of the ordered pairs is the domain of the function, and the set of all second elements of the ordered pairs is its range. Next, let's look at the relations given in tabular form. We need to determine which of them are functions. We know that for a relation to be a function, the elements in the first column should not be repeated. Since 2, 3, 4, and 5 are the elements of the domain of the given relation, having their unique image as 9, this relation is a function. Next, let's consider the second part. Here, element 2 corresponds to two different images, that is, 3 and 7. Thus, this relation is not a function. For a relation expressed using an algebraic rule to be a function, two distinct values of x substituted into it must generate distinct function values. That is, if a and b are any two values in the domain of a function, then a equal to b implies f of a equals f of b. Let's examine this using the examples. Relation f is defined from the set of real numbers to itself such that f of x is equal to 2x plus 5. Firstly, if x1 and x2 are real numbers, then so is 2x1 plus 5 and 2x2 plus 5. This satisfies the first condition, that every element in the domain set has the image. Secondly, if x1 and x2 are equal, then so are 2x1 plus 5 and 2x2 plus 5. Thus, every element in the domain has a unique image. So, relation f is a function. Let's check one more example. Is the given relation a function? Here, every positive real number x is associated with positive and negative root x. For example, x equal to 4 will have two images, positive and negative 2. So, it does not have a unique image. Moreover, negative numbers in the domain do not have any image in the codomain R. So, the domain R is not entirely used up. In this relation, both the requisite conditions for a relation to be a function are not met. This relation is therefore not a function. A relation f from a set A to a set B is said to be a function if every element of set A has one and only one image in set B. The understanding of the definition gives us a two-step test to find out whether a relation represented as an arrow diagram is a function or not. First, examine whether the first set is completely used up. Second, examine whether each element of the first set has only one image in the second set or not. For example, this relation is a function, as there is only one arrow coming from each element of the first set. This is a function too. There is only one arrow coming from each element of the first set. It just so happens that it's always related to the same element in the second set. It is for this reason that such functions are called many-one functions. This one is not a function. There are two arrows coming from the number 1. The number 1 is associated with two different elements in the range. So, this is a relation, but it is not a function. Look at this arrow diagram. What about that 16? It is in the domain, but it has no range element that corresponds to it. So, then, this is not a function. Just by looking at the graph, can we find whether it represents a relation or a function? As a matter of fact, there is such a method. It is called the vertical line test. For the vertical line test, we take a vertical line and place it on the graph. If the graph is a function, then no matter where on the graph you place the vertical line, the graph should only cross the vertical line once. For example, consider this graph. In order to determine if a relation given as a graph is a function, we place a vertical line on the graph and slide it all the way from the left to the right and find that it intersects the graph at no more than one point. Thus, this relation is a function. What about a common shape like a circle or an ellipse? It does not represent a function, as the graph crosses the vertical line more than once. We are now familiar with functions. A function is an association or mapping from one non-empty set to another such that it associates every element of the first set to a unique element of the second set. Set X of all the pre-images is the domain set, and the set of all the images is called the range set. A function whose range is either the set of real numbers or some subset of it is called a real-valued function. In addition to that, if its domain is also either the set of real numbers or some subset of it, it is called a real function. For example, consider this function f from the set of natural numbers to itself. Is it a real and real-valued function? Let us find the function values of x equal to 1, 2, 3, 4, and 5. On substituting these function values, we have found out the range as well. So this function is a real function because its domain is the set of natural numbers, which is a subset of the set of real numbers. It is also a real-valued function as all function values too are a subset of natural numbers, which is a subset of the set of real numbers. Here we shall deal with real and real-valued functions and learn how to find the domain and range for these functions when they are given as an algebraic rule. Domain of a real function f given by an algebraic formula is the set of all real numbers for which the formula makes sense and is defined. For example, the domain of f of x equal to 2x plus 5 is the set of all real numbers because fx is defined for all real numbers x. That is, we can find fx, which is a real number, for all real number values of x. Some functions, however, are not defined for all the real numbers and thus are evaluated over a restricted domain. We know that whenever we are dealing with fractions, we are not allowed to have 0 as the denominator, as that is not defined. So also when dealing with rational functions, we have to make sure the denominator is never equal to 0. Now the domain of a function consists of the values which the variable can take so that the function is defined. So with rational functions, if there is a number that will cause the denominator of the function to be equal to 0, we need to exclude it from our domain rather than checking it out for each number. For example, the domain of function f of x equal to 1 by x will be all real numbers except 0. In the same way, the domain of f of x equal to root of x is restricted because we cannot take the square root of a negative number. In general, there are two types of restrictions on domain: restrictions of an infinite set of numbers and restrictions of a few points. Square root signs restrict an infinite set of numbers because an infinite set of numbers make the value under the radical sign negative. But in the case of a rational function, a few points are restricted to prevent the denominator from becoming 0. Let us find the domain for some typical functions given in the algebraic form. A function f is a rule that assigns each element x in a set, x called the domain of f, exactly to one element f of x in a set, y called the range of f. The range is always found for the given domain. Early in our school days, we've all been taught to count objects using dots and introduced to the fractions by slicing things up. This makes for better comprehension and retention. This is because one remembers more when one forms connections with visual representations. Shall we form connections between some types of functions and their graphs so as to understand and assimilate them well? Let's start with the first function, called the identity function. This function maps each element of domain to itself. A function f from the set of real numbers to itself, such that f of x equals x for all x in the domain of f, is called the identity function. The identity function is like a mirror image. It maps each element of domain to itself. The domain as well as the range of the identity function is the entire set of real numbers. We can take a few values of x in the domain and find corresponding values of y. Using the ordered pairs obtained, we can plot the graph of this function. The graph is a straight line passing through the origin. Next is the constant function. This function takes each element of the domain to a constant. Constant function is defined as a function from a set of real numbers to itself, such that f of x is equal to c, a constant for each x in R. This function is called constant function, as for every value of x, the value of f of x is the same constant. A constant function gives the same output irrespective of input. This function can be thought of as somebody adamant about their decisions come what may. That is, whatever the input, the output will be the same. Here the domain of f is the set of real numbers R, and its range is a singleton set with element c. For example, let C be 3. As for any graph, we can take a few values of x in the domain. The corresponding value of y remains 3. Using the ordered pairs obtained, we plot the graph of this function. Let's plot these ordered pairs to get the graph of this function. As we can see, the graph of the constant function is always parallel to the x-axis. Let us move on to the third type of function, the polynomial function. Remember the polynomials of algebra. The polynomial function is actually a large family of functions that includes the identity and the constant function, which we have already discussed. It also, in fact, includes many more functions that we shall be discussing. A function f from R to R is said to be a polynomial function if f of x is equal to a0 plus a1 x plus a2x squared, so on, till an x to the power of n, where n is a non-negative integer, and a0, a1, a2, and so on till an are all real numbers. We call the term containing the highest power of x, that is, anx to the power of n, the leading term, and we call an the leading coefficient. The degree of the polynomial is the power of x in the leading term. The constant function, in fact, is a particular type of polynomial function whose leading coefficient is c, degree is 0. That is, the constant function is a polynomial whose leading term is c. The identity function, too, is a particular type of polynomial function whose leading coefficient is 1 and degree is 1. There are, in fact, various types of polynomial function. Shall we delve deeper into different types of polynomial function? Different degrees give rise to different polynomial functions. For instance, when the degree is 0, 1, 2, 3, the polynomial functions are called constant, linear, quadratic, and cubic, respectively. A linear function, as we have said, is a type of polynomial function whose leading term is a1x. Let us take the constants a1 and a0 as a and b, respectively, as is the convention. This gives us a standard linear function y equal to a, x plus b, where x is a real number, a and b are constants, and a is not 0. The domain as well as the range of the linear function is R, the set of all real numbers. Functions such as these yield graphs that are straight lines and thus have the name linear. The positions of line changes in the coordinate plane as the constants a and b varies. In the same way, a quadratic function is a type of polynomial function whose leading term is a2x squared. Let us take the constants a2 and a1 and a0 as a, b, and c respectively as per the convention. This gives us a standard quadratic function y equal to a, x squared plus bx plus c, where x is a real number. Here is something interesting about the quadratic functions. The word quadratus is the Latin word for square. Quadratic functions are useful in many applications in mathematics when linear functions are not sufficient. For example, the motion of an object thrown either upward or downward is modeled by a quadratic function. The graph of the quadratic function is called a parabola. Parabolas may open upward or downward and vary in width or steepness as the values of a, b, and c change, but they all have the same basic shape. Here, the domain of the function is R, and its range depends on whether the parabola opens up or down. If it opens up, then it's all numbers greater than or equal to the y-coordinate of the vertex. If it opens down, it's all numbers less than or equal to the y-coordinate of the vertex. Let us now discuss the polynomial function when its degree is 3, that is, the cubic function. A cubic function is a type of polynomial function whose leading term is a, 3x cubed. Let us take the constants a3, a2, a1, and a0 as a, b, c, and d respectively, as per the convention. This gives us a standard cubic function y equal to ax cubed plus bx squared plus cx plus d, where x is a real number, a, b, c, and d are constants, and a is not zero. The domain as well as the range of the cubic function is R, the set of all real numbers. The graph of the cubic function also behaves differently as the value of a changes, differently as the value of b changes, and as the value of c changes, and as the value of d changes. Going further, a polynomial function over a non-zero polynomial function is called a rational function. Rational functions are functions of the type f of x over g of x, where f of x and g of x are polynomial functions of x defined in a domain where g of x is not zero. If f of x is a constant function, 1, and g of x is an identity function x, then this rational function is called a reciprocal function. The domain is all real numbers except 0, and its range is also all real numbers except 0. The next type of function is the function which always gives a positive value. This function is called the modulus or absolute value function. The function f from R to R defined by f of x equal to modulus of x for each x belonging to R is called modulus function. For each non-negative value of modulus x, f of x is equal to x. But for negative values of x, the value of f of x is the negative of the value of x. Let us see the graph of the modulus function. The function always gives positive values, so its graph is above the x-axis. When x is positive, then the function is exactly the identity function in the first quadrant. When x is negative, the function value is the positive of the value that x takes. Together, the two branches make the graph of the modulus function look like a V of the English alphabet. Next is the signum function. The function f from the set of real numbers to itself defined by f of x equal to 0 when x is 0 and modulus of x over x for each non-zero x belonging to R is called the signum function. For x less than 0, the function takes the value -1. Similarly, the function takes the value 1 when x is greater than 0. This implies that the signum function takes only three values, namely -1, 0, and +1. Thus, the domain of the signum function is real numbers, and the range is the set with three elements in it, -1, 0, and 1. Let us see the graph of the signum function. The last type of function is the greatest integer function. This function is defined from real numbers to itself, such that f of x is equal to the greatest integer x for each x belonging to R is called the greatest integer function. True to its name, the function assumes the value of the greatest integer, less than or equal to x. This means that if the input is an integer, then this function outputs an integer. But if the input is a non-integer, then this function outputs the greatest integer just less than that. From the definition of greatest integer function, we can see that no matter what the value of x is, the value of f of x is always an integer. The domain of the greatest integer function is the set of real numbers R, and the range is Z, the set of integers. It is interesting to draw the graph of this function. Let's take some values of the function. Thus, the graph of the greatest integer function consists of infinite steps. The left endpoint of each step is included, and its right endpoint is excluded. The greatest integer function is also called the step function. This graph increases or decreases in steps rather than being a continuous line, and it also gives the appearance of steps, that is, where it gets its name, step function. Draw the graph of the function shown. Let's plot the graph of the function f of x. For positive x, its constant function is 4, and for negative x, it is -4. Draw the graph of the function shown. The function f of x is a combination of constant and linear functions. Draw the graph of mod x plus 1. The given function is an absolute value function, and any absolute value function takes positive values for positive x and negative value for negative x. Taking values of x and plotting it, we get the graph as shown. Draw the graph of the square root function. Taking the values of the positive square roots of x and plotting them, we get the values of x. Functions were once extensively used by scientists to describe physical processes. In the 18th and 19th centuries, scientists discovered that the elementary functions had their limitations. Solutions for some important physical problems, such as the orbital motion of planets, the oscillatory motion of suspended chains, and the calculation of the gravitational potential of nearly spherical bodies could not always be described in a closed form using only elementary functions. This created a need to develop the advanced functions from elementary functions. But how do we get the advanced functions from the elementary functions? Recall that we perform fundamental mathematical operations on numbers and variables. We will now perform these operations on functions to obtain the new functions that are required. So, we'll look at the algebra of real functions, that is, how to add, subtract, multiply and divide two real functions, and also how to multiply a real function by a scalar, which means a real number here. The four fundamental operations in scalar multiplication define the algebra of real functions. Let's go through each of the operations one by one. Let f and g be two real functions from a set X, which is a subset of R, the real numbers, to the set of real numbers R. Then the addition of f and g, denoted by f plus g, is also a function from X to R, defined as f plus g of x equal to f of x plus g of x for all values of x in the set X. For example, if x equal to x cubed and gx equal to 2x are two real functions, then the sum function f plus gx will be equal to x cubed plus 2x. As you can see, the sum of the two real functions is yet again a real function, so we can plot a graph on the Cartesian plane. Let us first plot the f and g functions and then their sum function in one graph. Now, let's look first at the graph of f(x) equal to x cubed, and on the same graph gx equal to 2x. Then, on the same graph, the sum function f plus gx equal to x cubed plus 2x. Notice the shape of the graph. Let's check the value of the functions f of x, g of x, and f plus g of x at x equal to 1. The sum of the function values of x equals to 1 is equal to the value of the sum function at x equal to 1. Let's consider one more example. We are to plot the graphs of f, x, gx, and f plus gx. Then, we need to show that the y-coordinate of the point corresponding to x equal to 1 on the graph of y, the sum function, is the result of adding the y-coordinates of the two given functions. We begin by finding the sum function. Now we plot the graphs of f(x), gx, and f plus gx. Now, from this graph, we need to find the y-coordinate of the point corresponding to x equal to 1. For that, on the graph, through x equal to 1 on the x-axis, we draw a perpendicular line. We mark the point of intersection of each curve with this perpendicular line. We now need to find the y-coordinate of these three, the points of intersection of the line x equal to 1 with each of the curves. So, from the 3 points of intersection, we draw perpendiculars to the y-axis. Now, from the y-axis, we can see that the y-coordinates of the f and g functions are 3, and the y-coordinate of the sum function is 6. Thus, the y-coordinate of the point corresponding to x equal to 1 on the graph of y, the sum function, is the result of adding the y-coordinates of the two given functions. Generalizing, the y-coordinate of each point on the graph of y equals f plus gx is the result of adding the y-coordinate of g of x to the y-coordinate of f of x. We may say that adding two functions is like plotting one function and taking the graph of that function as the new x-axis. Points of the second function are then plotted with respect to the new axis. Just as with addition of real functions, we can define the subtraction of one real function from another by substituting addition for subtraction. Recall that subtraction is the reverse of addition. Let f and g be two real functions from a set X, which is a subset of R, the real numbers to the set of real numbers R. Let the subtraction of f and g be denoted by f minus g, which is a function from x to r, defined as f minus g of x equal to f of x minus g of x for all x in their domains. For example, if x equal to x cubed and gx equal to 2x are two real functions, then the function f minus gx will equal x cubed minus 2x. The difference between the two real functions is also a real function, of which we can plot a graph. Let's look at the graph of the difference function. As before, the graph of fx equal to x cubed and gx equal to 2x is plotted on the same graph. Then on the same graph, the difference function f minus gx equal to x cubed minus 2x is plotted. Notice the graph. The y-coordinate of each point on the graph of y equal to f minus g of x is the result of subtracting the y-coordinate of g of x from the y-coordinate of f of x. Further, the sum function f plus g and the difference function f minus g will be defined when both f and g are defined. So we can say that the domain of each of these combinations is the intersection of the domain of f and the domain of g. In other words, both functions must be defined at a point for the combination to be defined. Let's consider the functions f of x equals x squared, g of x equals 2x plus 1, and find out the domains of their sum and difference. We have two real functions. We add them and subtract g from f to get the two required functions. Notice that here there are no like terms that can be simplified. It is given that f and g are two real functions. This means that their domains are either R or a subset of R. But in this case, it is possible to evaluate the function for any element of R, making it the domain. This common domain of f and g is also the domain for the sum and difference function. Next, let's move on to the third operation, scalar multiplication. Here by scalar we mean involving a real number. Let f be a real valued function from set x, which is a subset of real numbers, to set of real numbers R, and k be a scalar. Then the product kf is a function from x to R defined by kf of x equals k times f of x for each element x of set x. For example, if f is a function from the set of real numbers to itself such that f of x is 2x, then find 3f of x. 3 times f of x gives 6x. Let us now draw the graph of f of x and 3f of x. Let us now draw the graph of 2x and then 6x on the same coordinate plane. Notice the shape of graph on the function and its scalar multiple. Here the shape of the graph is the same. For any given value of x, the y-coordinate appears 3 times in the function 3f of x. Consider another example. Now, a real function is defined by x over alpha. We need to find the indicated scalar products and mention their domains. Now, alpha fx will be alpha multiplied by x over alpha, giving x, which is defined for all real numbers, which then is the domain for the function alpha fx. Similarly, alpha squared fx will be alpha squared multiplied by x over alpha, giving alpha x, which is also defined for all real numbers, forming the domain for the function alpha squared fx. Now 1 over alpha fx will be 1 over alpha multiplied by x over alpha, giving x over alpha squared. This too is defined for all real numbers, the domain for the function 1 over alpha fx. We have now learned to add and subtract two given functions and also multiply a function by a scalar. Let us now learn how to multiply two functions. The product of two real functions f, a function from x to r, and g, also a function from x to r, is a function fg from x to r, defined by f g of x equal to f of x multiplied by g of x for all elements sx belonging to set x. This is also called pointwise multiplication. Given two real functions, we need to evaluate their product function. Here is the multiplication of these two functions. Let's now draw the graph of the functions f, g, and fg. We draw the graph of the quadratic equation f of x, then the linear g of x, and finally the cubic function fg of x on the same plane. Notice that the function value of the product at a point is the product of function values of functions fx and gx. This brings us to the last point, the quotient of two functions. Let f and g be two real functions defined from a set x, which is a subset of real numbers, to the set real numbers. The quotient f over g is a function defined by fx over gx, provided g of x is non-zero and element x belongs to set x. Let's look closely at the operation by taking the example given, two functions f of x and g of x. Let's find their quotient. We divide root x by x cubed to obtain the quotient function. Now we plot the function f of x, then g of x, and finally their quotient on the same set of axes. Notice that the quotient function is not defined at 0, so the domain of the quotient function is the common domain of f and g, except when g is 0. A particular case of the quotient of two real functions is the reciprocal function, where the domain will be all elements of the set x, except the ones that make f of x 0.